We're going to now begin our discussions on cardiac function or heart physiology. Please continue to work on the heart anatomy while we get into the heart physiology. Heart physiology can be a tough area. It's a hard topic. It's easier if you understand completely the anatomy of the heart and blood flow through the heart. It's very important for your clinical knowledge to better understand how individuals with cardiac problems are treated. But I'm going to remind you of cardiac muscle a little bit before we move on to the electrical activity of the heart. You should have learned in A&P1 that there's three types of muscle: skeletal, cardiac, and smooth. And cardiac muscle tissue is a striated muscle in that it has a similar striping pattern as skeletal muscle. The cells are branched in shape as opposed to cylindrical like the skeletal muscle cells. And these branched cells attach to one another. And what these attachments allow is a communication from one cell to another. And this cell communication is largely in the form of an electrical activity. So the heart muscle can actually transmit electrical current through the tissue from cell to cell. What this allows is the muscle to contract kind of in unison in order to produce a powerful contraction of the heart. This is all autorhythmic, so the heart will beat automatically. It doesn't need to be told when to do this by, say, nerves. There are nerves attached to the heart, but those nerves are just to speed the heart up, slow the heart down, and make it pump harder. It doesn't initiate the contractions. The contractions are controlled by a small piece of tissue in the right atrium. You've probably heard of pacemaker, but we're going to call it the sinoatrial node. And once that sinoatrial node depolarizes, that's another word you should have learned in A&P1 when you studied neurons. Depolarization is when the cell goes from a resting negatively charged state towards more of the positive charged state. And when muscle depolarizes, that leads to the contraction. So a good rule of thumb is depolarization triggers contraction. So the sinoatrial node is going to depolarize, but then that depolarization needs to spread throughout the atria. And it does this through the muscle cells. The muscle cells will transmit this depolarization from cell to cell throughout the atria. And this depolarization of the atria is going to then lead to them contracting and helping to push blood down to the ventricles. So the pacemaker is first, then the atria depolarize, and then after that they're going to contract. While they're contracting, we need to start thinking about the ventricles. And there's going to be a little bit of a delay that occurs because we want those ventricles to fill. That delay occurs at what's known as the AV node, the atrioventricular node. And that AV node also helps to send the signals down into the ventricles. And there's a little path extending from the AV node called the bundle of His. And this is the only place that electrical current can get from those atria down into the ventricles. So it's a very important small little pathway for the electrical current. Keep in mind, all these lines in here are representing electrical pathways. They kind of look like blood vessels, but they're not. They're electrical current. Once the electrical current travels into the bundle of His, it divides into two branches, the right and left bundle branches, which are going to service the right and left ventricles. These action potentials, these waves of depolarization are going to travel towards the apex, which is the point of the heart, and then spread throughout the ventricles in what's called the Purkinje fibers. So Purkinje fibers are specific paths within the ventricles for this electrical current to travel. And once it gets to the Purkinje fibers, that's going to cause ventricular depolarization. The ventricles depolarize and then they contract. So notice this is a coordinated pathway. It has to occur this way in order for the atria to contract first, then the ventricles. And then another signal will come from the pacemaker, and it'll happen all over again. So every time your heart beats, electrical current travels from the SA node to the atria, to the AV node, down the bundle of His, separates into branches, gets to the ventricles, and depolarizes the ventricles. So collectively, this is called the cardiac conduction system. It can be sped up by a number of things, like your sympathetic nervous system will speed this up, speed up your heart rate. Epinephrine and norepinephrine in the bloodstream will speed this up. So adrenaline will speed up your heart rate. Thyroid hormones will actually influence your heart rate. So an individual with hyperthyroidism will often display a fast resting heart rate. So your heart rate is affected by a number of things. Age can affect your heart rate. Young children actually have a fast heart rate. Then it slows down, and then as we get old, elderly individuals tend to have a slightly faster heart rate. There's a number of ions that will affect your heart rate. We're going to be talking about those later on, but calcium's a really important one. The more calcium your heart has, the more it beats. The less calcium, the slower and weaker it'll beat. So a lot of things will influence this cardiac conduction system. And I recommend you going to Canvas and watching this animation. We can detect the cardiac conduction pathway using an instrument. This instrument is called an electrocardiogram, often ECG for short, or EKG. And what an ECG will read is this change of electrical current throughout the heart. And it's set up a certain way. There's electrodes that are placed on the body, and you get an output. You get these what are known as tracings. And we've probably all seen these tracings somewhere at some point in our life. And these tracings tell us about the electrical activity transmitting through the heart. So you can learn a lot from a heart with an ECG. We're going to learn what each of these little waves, what each of these little peaks and intervals mean. And this is your textbook's detailed version of a single cardiac cycle. So that means this is one heartbeat. And you can imagine after it would be another one. So every time a heart beats, you get this output. And we're going to learn that there's, in essence, three major waves. There is the P wave. There's a complex one called the QRS, but you can kind of think of that as one. And then there's a T wave. There's also some intervals and segments. So, for example, the PQ interval is just from the start of the P to the start of the Q. The ST is at the kind of end of the S to the start of the T. QT is from the start of the Q to the end of the T. So these are all intervals in time that can change. So all these things can change based on maybe problems with the heart electrical activity, and we call those arrhythmias. So we really need to work hard on looking at one of these tracings, understanding that there are letter designations for the waves and the intervals, and then start to put this together and understand what's causing those waves and intervals. So for instance, the P wave. The P wave is seen whenever the atria have depolarized. So you can kind of imagine that right before the P wave is going to be where the pacemaker fires. So the pacemaker is going to fire somewhere around here, and once that electrical current enters the atria and depolarizes them, you're going to see a P wave. So that P wave tells you that the atria are depolarizing, and right after that, they're going to contract. So notice that on this figure, they show this blue bar representing this interval, basically right at the top of the P until just about at the Q of the QRS. That's where the atria are going to be contracting. Now notice, you don't detect contraction. You detect depolarization. Electrical current is what the ECG detects. So you kind of have to assume that if you have a P wave, the atria are going to contract right after that P wave, or during the P wave and just after the P wave. So that's the P. The QRS represents the ventricular depolarization. Now the reason why it's a little more complicated is the right and left ventricles depolarize at a slightly different time. So you get a little bit of a more complicated look to the QRS. We're not going to really get into that, but that's why it's a little more dramatic looking than the P. It's also bigger because there's just a lot more muscle in the ventricles than there is the atria. But the QRS represents ventricular depolarization, and then following that QRS, you would assume that the ventricles are going to be contracting. So this yellow bar represents the time interval that the ventricles are contracting. And then finally, the T wave represents ventricular repolarization. Now, repolarization, if you remember, is when a cell, or in this case tissue, goes back to rest. All right, so it goes back to a negative charged interior. And repolarization happens after every depolarization. Now you only see on an ECG the ventricular repolarization. The atria repolarize during the QRS. But since the ventricles are so much bigger, you see that and you don't see the atria repolarizing. Okay, so this might be a lot to chew on, but think about these three waves, and then we're going to revisit this in the next video when we go over this figure and kind of walk through it once again.